There are basically 5 ways a star can blow itself apart, and the last might be happening 150 light-years from Earth. Every type of supernova, bluntly explained in 10 minutes. No filler, no jargon without an immediate translation. Here's the thing. When people say supernova, they usually picture one explosion. There are at least 8 distinct flavors, different triggers, different victims, different corpses left behind. One of them could be cooking in our sky right now. I'll bluntly walk you through every one. No jargon without translation. No mystical narration about cosmic beauty. Just the raw mechanics of massive stars tearing themselves apart under their own gravity and physics. 2 families to remember. That's it. Thermonuclear supernovae, a dead star pushed past a fusion tripwire. And core collapse supernovae. A massive star runs out of fuel and its core caves in under its own weight. Everything else is just subcategories of those 2 families. Remember that split. It makes the rest simple. Astronomers also slap on spectral labels, Type 1 and Type 2. And the split is stupidly simple. If the explosion shows hydrogen in its light, it's Type 2. If not, Type 1. That's the whole distinction. Sounds trivial until you realize hydrogen is the most common element in the universe by a huge margin. A star exploding without it means something violent already stripped its outer skin off before the boom. 8 flavors coming, from what astronomers trust most to what barely makes sense. Starting with the reliable one. Type 1a, the workhorse of cosmology. It starts with a white dwarf, the burned-out corpse of a sun-like star, Earth-sized but crammed with the mass of the sun, not fusing anything. Basically, a stable diamond of carbon and oxygen. Then it eats, usually from a companion star it's orbiting. It siphons off hydrogen and helium, piling on mass. Here's the thing about white dwarfs. They have a hard weight limit, about 1.4 times the Sun. It's called the Chandrasekhar limit, named after the guy who worked out the math on a boat to England. Cross that limit, and carbon fusion ignites. Not on the surface, but deep inside the core. White dwarfs are held up by weird quantum pressure that ignores temperature. So the fusion doesn't calm the star down. It runs away. In about 1 second, the entire star fuses into heavier elements. The whole thing vaporizes. Nothing left behind. No neutron star, no black hole. Just an expanding cloud of freshly minted iron and nickel. Why care? Because every Type 1a explodes at roughly the same brightness. Same trigger, same mass, same boom. That makes them standard candles, cosmic mile markers. Measure how bright one looks from Earth, you know its distance. That's how we mapped the expansion of the universe, and how we discovered dark energy in 1998. 2 teams, same method, same result. 2 Nobel Prizes, all from watching one type of star blow up. Small catch, though. Astronomers still argue what detonates these. One camp says single degenerate white dwarf eating a companion. The other says double degenerate, 2 white dwarfs spiraling in and merging. Both probably happen. Both look identical from afar. Now strip the hydrogen off a bigger star, things get messier. Next up, types 1b and 1c. These are core collapse events wearing a disguise. The star was massive, 20, 30, 40 times the Sun's mass. Before exploding, it lost its outer layers, blown off by fierce stellar winds, or stripped by a close companion. The difference between B and C is basically what got stripped. Type 1b lost hydrogen, kept its helium shell. Type 1c lost both. No hydrogen, no helium in the spectrum. It's a naked stellar core going off. The usual suspects are called Wolf-Rayet stars. Bluntly, these are stellar exhibitionists. Enormous, hot, shedding layers violently. They blast material outward at thousands of kilometers per second. By death, half their original mass is gone. What's left collapses. Same physics we'll hit in Type 2. Iron core, sudden implosion, rebound explosion outward. Here's where it gets interesting. Type 1c, the fully stripped version, is linked to long gamma-ray bursts. When one of these bare cores collapses fast enough and spins hard enough, it doesn't just explode outward. It fires twin jets at near light speed along its rotation axis. If one points at Earth, we see it. For a few seconds, a gamma-ray burst outshines every star in the observable cosmos combined. Brightest event known. Put the hydrogen back, and you get Type 2, the classic explosion people picture when they say supernova. A red supergiant, a bloated, aging monster 10 to 50 times the Sun's mass, runs out of fuel. It's burned hydrogen for millions of years, then helium, carbon, heavier stuff, each stage shorter than the last. The final stage, silicon fusing into iron, lasts about a single day. And iron is the dead end. Fusing iron doesn't release energy, it absorbs it. The moment the core turns iron, the fire goes out. Gravity wins. The core collapses from the size of Earth to a small city in about a quarter second. It hits nuclear density and rebounds hard. A shock wave rips outward through the star's dying outer shells. A blast of neutrinos, 99% of the released energy, kicks the outer layers clean off the star. What's left in the middle is either a neutron star, essentially a city-sized ball of pure neutrons, or, if the star was heavy enough, a black hole, an event horizon swallowing everything nearby. Type 2 comes in flavors, sorted by how the brightness fades over the following weeks and months. Type 2p sits at a plateau, stays bright about 100 days as the hydrogen shell recombines. Type 2l drops linearly. Boring names for what's happening. Astronomers weren't hired for their branding. The textbook Type 2 happened in 1987, Supernova 1987A, in the Large Magellanic Cloud. 168,000 light-years away, the first supernova visible to the naked eye since 1604. Neutrino detectors on Earth caught the pulse of neutrinos about 3 hours before the light itself arrived. Neutrinos escape the collapsing core immediately, while light has to fight through dense outer layers on the way out. That single event basically confirmed our entire theory of how massive stars actually die in the end. Everything so far was normal. Now it gets weird. Types 2n and 2b, same core collapse engine, different environment. Type 2n. The N stands for narrow, because the emission lines in its light aren't moving fast. Weird for an explosion. Before dying, the star coughed off huge amounts of gas into a dense surrounding shell. When the supernova shockwave finally punches into that shell, it lights up the stationary gas from behind. Result? A supernova that stays bright for months or years. An explosion continuously slamming into a wall. Type 2b is the shapeshifter. Starts out looking like a normal Type 2, with hydrogen in its spectrum. Then, within weeks, the hydrogen fades and it starts looking like a Type 1b, helium dominant, no hydrogen. Basically, the star had almost all its hydrogen stripped off, but not quite all. A thin skin remained. Once the explosion burns through that thin skin, you're looking straight at the naked stellar core underneath. We've actually caught progenitors of some 2Bs in old Hubble Space Telescope images from before they exploded. Pictures taken years earlier, where you can go back and identify the exact star that later blew up. It's forensic astronomy. The corpse is fresh. And here's the thing. We have baby photos of the victim. These were loud explosions. The next one is different. A slow-motion suicide unfolding across 1,000,000 years. Pair instability supernova. The strange one. Almost mythical. Only happens to monsters, stars over 130 solar masses. These giants don't really exist anymore. The elements needed to form them without self-destructing in adolescence got too polluted. Here's the mechanism. In the core, temperature gets so extreme, the gamma rays start spontaneously converting into electron-positron pairs. Sounds cool. Also catastrophic. Those gamma rays were holding the star up against its own crushing gravity. Their pressure. Convert photons into mass, and the pressure drops. The core suddenly can't support the enormous weight sitting above it. The star collapses. Compression heats the core. Runaway oxygen fusion ignites, not gently, but as a nuclear explosion. Here's the thing about a star that big. It doesn't just eject its outer layers like a normal supernova. The fusion releases so much energy so fast, the entire star gets unbound. Every single atom blown into space. No neutron star left, no black hole, nothing. Just an expanding cloud where a giant used to be. Best candidate we've seen is supernova 2006 GY, about 100 times brighter than a normal supernova, stayed visible for over a year. The energy involved is genuinely absurd, basically unmatched by anything else we've catalogued. These things were common in the early universe, when first-generation stars of pure hydrogen and helium could grow massive. Even brighter exists, and it barely makes sense. Superluminous supernovae. This is the payoff of the whole ranking. These things can be 10 times, sometimes 100 times brighter than a standard supernova, and nobody knows why. Two leading theories. First, the magnetar hypothesis. Sometimes core collapse forms not a normal neutron star, but a magnetar. A magnetar is a neutron star with a magnetic field about 1 trillion times stronger than Earth's own field. Spinning at hundreds of rotations per second, it acts like a colossal battery, pumping energy into the surrounding debris. Second theory. Same idea as Type 2N, but bigger. Massive gas shells, explosions slamming in, kinetic energy becoming light. Some are probably both mechanisms. But here's where it gets weirder. Sometimes massive stars don't explode at all. Astronomers have caught cases of massive stars that just disappeared. One frame, red supergiant. Next frame, nothing. Gone. No supernova, no brightening. These are failed supernovae. The core collapses directly into a black hole, silently. 20 solar masses of star erased from the sky, no fireworks. And then there's the outlier, the killer nova. Not from a single star, two neutron stars, corpses from previous supernovae, spiral together and finally merge. The collision is 1,000 times fainter than a supernova. That's why we call it a killer nova, essentially. But it does something no supernova can. It forges gold, and platinum, and uranium, the heavy elements. Most of the heavy elements on the periodic table were made in these mergers, not in ordinary supernovae. We saw one directly in August 2017. Event GW 170817, to be exact. Gravitational wave detectors picked up two neutron stars merging. Seconds later, telescopes caught the flash of light. First time in history, we watched the same event with gravity and light. Multi-messenger astronomy was born. Also, humanity officially confirmed where gold actually comes from. Two dead stars smashing into each other. So what does any of this mean for you down here on Earth? Basically, everything you're made of. Every atom in your body heavier than helium was cooked inside a star and blasted into space by supernovae. The calcium in your bones, the iron in your blood, the oxygen in every breath, all of it. Cooked in stellar cores over billions of years before settling into the cloud that became our solar system. You are, quite literally, supernova debris that got lucky enough to eventually become self-aware. That's the whole story. Nearest supernova candidate? Betelgeuse, the red star in Orion's shoulder, about 640 light-years away from here. Could go tomorrow. Could go in 100,000 years. Either way, bright as a full moon for months. Also, completely harmless to us. Eta Carina is more interesting. 7,500 light-years away, wildly unstable. Already had one massive outburst back in the 1800s. It'll probably go pair instability or superluminous. It'll be genuinely spectacular when it finally does. And essentially, still completely harmless to us down here. The safe distance for a normal supernova is roughly 50 light-years. Any closer strips our ozone. Get inside that radius and the radiation triggers a mass extinction. Nothing on our list is that close. Here's the thing. The real threat isn't the supernova itself. It's a gamma-ray burst aimed straight at Earth. Those Type 1c jets I mentioned, one firing from a few thousand light-years away, ruins our day. Some paleontologists suspect a gamma-ray burst caused the Ordovician mass extinction 440 million years ago. We don't know for sure, and that's the point. These things stay quiet until they aren't. One more thing before you go. Remember the pair instability supernova? The one that erases the entire star? A few are probably going off across the observable universe every year, right now, as you watch. Their light hasn't reached us yet. One might already be inbound, its photons crossing the final light year now. I bluntly explain space stuff like this every week. Hit subscribe and stick around for the next one. Next up, how black holes actually kill you. Spoiler.